Have you ever watched a basketball game, seen a player sink a perfect shot, and just wondered, how? I mean, it looks like pure artistry, right? But it's also pure physics, and it's all described by the language of calculus. So today, let's break down the math behind that perfect swish. So what really is the secret? Is it just endless practice, raw talent? Yeah, sure, that's part of it. But from a mathematical point of view, what are we actually looking at? The secret isn't just in the release or the follow-through, it's in the actual flight of the ball.
The absolute key to a shot that just swishes right through the net is this beautiful, perfect parabolic curve. And what's so cool is that we can analyze this arc with incredible precision. We can understand every single moment of its journey, from the player's hand to the basket.
And that brings us right to our first section, calculus on the court. We're about to take math right out of the textbook and put it on the hardwood.
You see, that arc isn't just some random shape. We can perfectly describe the ball's path using a mathematical function. And the toolkit we use to break that function down, to find its highest point, its speed, its direction at any given instant, well, that's the power of calculus. So how in the world do we do that? We start with a really fundamental tool, one that helps us understand the steepness of the ball's path at any single moment. And that tool is called the derivative. Now, the formal, textbook definition is the instantaneous rate of change. But here's a much easier way to think about it. Imagine you could pause the basketball mid-flight. At that exact split second, you draw a straight line that shows its direction. The slope of that line is the derivative. It's that simple. So for our jump shot, the derivative is basically giving us the exact steepness of that arc at any point in time. Is the ball rising fast? Is it kind of flattening out at the top? Or is it dropping down towards the hoop? The derivative gives us a precise number for that steepness, right then and there. Now, finding this derivative isn't just guesswork. There's a set of established rules, almost like a coach's playbook, that tells us exactly how to deal with different kinds of functions. So let's run through the key plays. First up is the power rule. This is your fundamental go-to play. It's for any simple function where you have a variable raised to a power, like x squared. All you do is bring that exponent down to the front and then subtract 1 from the original exponent. It's simple, it's fast, and it is super effective. But okay, what if our function is a bit more complex? What if you have two different functions being multiplied together? For that, we need a special play called the product rule. The pattern is pretty straightforward. You take the derivative of the first part, multiply it by the second part as is. Then you add the first part as is, multiplied by the derivative of the second. Let's look at a quick example to make that real. Say our function is 3x squared times sine of x. We can't just guess here. We apply the product rule. The derivative of 3x squared is 6x, so you get 6x times sine of x. Then you add the first part, 3x squared, times the derivative of sine of x, which is cosine of x. See? It's just following the play, executed perfectly. Our playbook also has a move for division. If you've got one function divided by another, you use the quotient rule. There's actually a classic little rhyme for this one. Low d high minus high d low, square the bottom and away we go. It's just a pattern. The bottom function times the derivative of the top, minus the top function times the derivative of the bottom, all of that over the bottom function squared. And for our last major play, we have the chain rule. This one is for those nested functions. A function that's living inside of another function, kind of like those Russian nesting dolls. The trick is, you take the derivative of the outside function first, leaving the inside part alone, and then you multiply all of that by the derivative of the inside function. For instance, look at sine of 6x squared minus 5x. The outside function is the sine part, and its derivative is cosine. So you get cosine of 6x squared minus 5x. Then you multiply that by the derivative of the inside stuff, which is just 12x minus 5. The chain rule lets us unpack these complex functions one layer at a time. So here's a quick look at our playbook. We've got the power rule for simple terms, the product and quotient rules for when things are multiplied or divided, and the chain rule for those nested functions. These are the core tools, the whole shebang we need to analyze just about any shot. Okay, playbook in hand, let's get back on the court. It is time to use these rules and actually analyze the flight of the basketball and see what it tells us. And this is where the derivative really becomes a storyteller. When its value is positive, it means the ball's slope is positive, it's rising. When the derivative's value is negative, the ball is falling. But what about that moment when the derivative isn't positive or negative?
What happens when it's exactly 0?
That's the magic moment. It's that split second where the ball seems to just hang in the air. As it transitions from going up to coming down, its slope is perfectly flat. That is the peak of the shot, its highest point, and it's precisely where the derivative equals 0.
And we can even go one step further. If you take the derivative of the derivative, which is called the second derivative, it tells you about the shape of the curve itself, its curvature. A jump shot always has this downward-facing bowl shape, which in calculus we call concave down. And that consistent curvature is what makes the arc so predictable.
So it is definitely cool that we can analyze a jump shot with this much detail, but let's zoom out. Why does any of this really matter beyond the basketball court?
Well, the truly amazing thing is that this exact same playbook, the power, product, quotient, and chain rules, they aren't just for sports. These are the very same tools used to model changes in the stock market, to design the most efficient airplane wings, and yeah, to calculate the precise trajectory you need to send a rocket all the way to Mars.
When you really think about it, from the flight of a basketball to the orbit of a planet, calculus is the fundamental language we use to describe, analyze, and optimize our world, a world that is constantly in motion.
So we just broke down the physics of a perfect jump shot, but the applications for these tools are truly endless. So I'll leave you with this question. Now that you have the playbook, what changing system in the world would you want to analyze next?